Okay, I'm going back to my standard greeting. So hello, this is Mr. Howard. In this video we're going to continue our look at polynomials and specifically being able to identify the end behavior, the roots, and then in this video we're going to add the sketching. So we're going to look at specific examples and actually make a rough sketch at the end. So here is an example, and I have gone ahead and added these steps in. We'll use these steps each time. We need to follow this so that we can get this done. So step one is to factor, if not already factored. Well, in this example, x minus 4, x plus 5, this is already factored for us. So step one is actually already done. Step two, we need to identify the roots, including the type of root, whether it's single, double, or triple. So remember, when we're identifying roots here, you take the whole function and set it equal to 0. So if we set this equal to 0, that means either this has to be 0 or this chunk has to be 0. Okay, so if we do that, we have x minus 4 equals 0, so x equals 4. And then we have our other x plus 5 equals 0, so that means x equals negative 5. We're just solving for x there. So our roots are 4 and negative 5. And notice that these are to the power of 1 here. We have an implied power of 1 here and an implied power of 1 here. So I'll put those in there. And for that reason, these would be considered single roots. Okay? So single roots, so we have 2 single roots of 4 and negative 5. Alright? So step 2 is done. Step 3, identify the end behavior. Okay, to identify the end behavior, we need to go ahead and expand this back out. I already know that you can tell that this is a quadratic. So if we expanded this out, it would become x squared. I'll draw arrows here so you know what I'm doing. If we expanded that out, we would have x squared. That would be a minus 4x and a plus 5x, so that would just be plus x. And then negative 4 times 5 is negative 20. So if we expanded this out, we'd have x squared plus x minus 20, and that would give us a degree 2 polynomial, right? This is a quadratic. You knew that already from looking at this in your previous experience. But remember that a degree 2 polynomial has the end behavior like this. And notice the squared term, the one that determines our degree, is positive, so it's going to have the end behavior of up and to the left and up and to the right. Okay, so our end behavior looks like this: up and to the left, up and to the right, and that's based on this being a power of 2. So now we can roughly sketch our graph. Now we could be very specific about this graph based on our knowledge of quadratics and find the vertex and all of that, but we're not really interested in that right now. We're only looking to make rough sketches of these polynomials. So we're going to put a root over here at negative 5, and we're going to put a root over here at positive 4. And we know that the end behavior looks like this, so it's opening upward like that. And then we're just going to sketch it in here. So something like this. Alright, that's not perfect, but it would look something like that. So remember, this is our end behavior right here. Notice it looks like this: up and to the left, up and to the right. Alright, and that's based on something you already know with a quadratic. So we followed all of the steps here. Alright, so let's look at another example. All right, we have example 10 here, and this one is an example that has a double root. So we have 2x times the quantity x minus 3 squared. And I'm going to go ahead and rewrite this. Technically, this is already factored, but I'm going to go ahead and rewrite this as 2x times this x minus 3 quantity squared means this, x minus 3, x minus 3. All right, just like that. This is equivalent what we started with, but I want you to see when you have this power of 2 right here for this x minus 3, that is where our double root is coming from, because notice when we break this thing down and we set it equal to 0, that means that either 2x is equal to 0, so divide by 2 here and we get x equals 0, or x minus 3 has to be equal to 0. We have two of those, so technically we could go ahead and do this twice. So we have x equals 3 and x equals 3. And this is where our double root comes from. Okay? That's why we have a double root. That's why it's called a double root. Alright, so let's go ahead and write these out. So we have a x equals 0 is a single root, and x equals 3 is a double root. Okay, so that part's done. Now we need to identify the end behavior. So a quick rule of thumb is, see how we have a power of 2 here, and then we're multiplying this power of 2 portion by a power of 1. Well, that's going to give us a cubic when we're done. So I think that's actually a little faster, but I want to go ahead and expand this all the way out so that you can actually see it fully expanded, so that you can see that it is in fact a degree 3, and it will be a positive degree 3, but let's just go ahead and expand all of this out. So we would have 2x, and then if we expanded this x minus 3 quantity squared, this part out right here by doing this right here, we're going to get x squared. Minus 3x and minus 3x would give us minus 6x. And then negative 3 times negative 3 is a plus 9. Okay, now we do this. So we distribute that 2x in, and we would finally end with a 2x cubed minus 12x squared plus 18x. Alright, so once we're completely done with that, you can see that we do have a degree 3 polynomial. Alright, so we have a degree 3 polynomial, and the coefficient is positive for this, so we have a positive third degree polynomial. That means our end behavior is going to be up to the left and down, up to the right and down to the left. So our end behaviors look like this. The right side looks like this, the left side will look like this, because it's the same as the cubic parent function. Okay, the end behavior being here and here. Alright? Okay, now I think this is probably can be the most difficult to understand in the beginning, but now we need to graph it. So we've identified the end behavior, and remember that comes from the degree and the whether it's positive or negative. And then step 4, we're going to go ahead and graph it. So let's do that. So we draw in a graph here. We know our end behavior. If I go ahead and we'll have to possibly move this in a minute, but just so we don't forget, our end behavior looks like this. At the very end, it's going to look like this and like this. Now we need to put our roots in. So we have a single root at 0. So that means, I'm going to do that in pink so we can see it. That means we're going to cross through the x-axis completely. We're going to pass completely through it. Then we have a double root at 3. So this one right here is going to be a double. Alright, so the only way, here's the key, the only way that we can have end behavior like this and cross through these roots, I'm going to have to squish this in now. So our end behavior is going to be like this, and I scooted this in so that we can make this cross. So I've got to come up through here, cross completely through. So I have a single root right there. Alright, now in order to get back to here, and this is my double root right here. Should have labeled that in the beginning, double. In order to get back here, I've got a curve. Now, how high this curve occurs, this curve back down, we don't know. We can find that when we get to calculus, or we could use a calculator, but it doesn't matter for our rough sketch. So we know we have to turn back down. Now, I can't cross through. This is a double root, so this is going to be a sit double root. I'm going to come down here, go tangent to the x-axis, and curve back up. Okay, so I come down, a bump, or I have a sit like that, not a bump, and I finish like that. Okay, so the end behavior is in place, down and to the left, up and to the right. I have a single root at x equals 0, so that all looks good, and then I have a double root at 3, so that's a sit double root at 3. Okay, and then we'll label this one single, x equals 0, double at x equals 3. And we'll erase our original end behavior because now we have our graph that looks pretty good there. Alright, so let's move to the next example. Alright, here we have example 11, and this is an example of a function with a triple root this time. So we have negative x times x minus 5 quantity cubed. Alright, so this power of 3 right here for this x minus 5 factor right here is actually going to be where our triple root comes from. Step 1 says factor if not already factored. This is actually factored so that we can identify our roots. I'm going to go ahead and expand the x minus 5 quantity cubed out. I'm going to break that into 3 separate factors here. Technically this is factored, but I'm going to rewrite it as negative x, and x minus 5 quantity cubed actually means x minus 5 times x minus 5 times x minus 5. Alright, we have 3 different x minus 5s, which is the same thing as x minus 5 quantity cubed. Alright, so the next thing that we need to do, we're identifying, this is already factored, we're identifying our roots here. So we set this whole thing equal to 0, so that means that negative x is equal to 0 or x minus 5 is equal to 0. So here x equals 0. Just you would divide by negative 1. 0 divided by negative 1 is still 0. So x equals 0 here. So that's a single. And x minus 5, we actually have 3 of these. So x minus 5 equals 0. X minus 5 equals 0. We're all going to get the same answer. So it's x equals 5. You would just add 5 to both sides there. So x equals 5, and that is a triple. Okay, it's a triple because we have 3 of them. Alright, so we have a single root at x equals 0, and we have a triple root at x equals 5. Alright, so that part is done. Now we need to identify the end behavior. Alright, if we have this x minus 5 quantity cubed, our highest degree is going to be a 3 for that part. Okay, x minus 5, if you multiplied this all out, you would get a cube term there from that. And then we still have this negative x out here, so it's going to be negative x being distributed in, and we're going to get a negative x to the 4th. So we actually have a degree 4 polynomial. 3 of it comes from right here, and 1 of it comes from here. So together, that's going to give us a 4th degree polynomial, and it will be negative. So we're going to have the end behavior of that of a negative x to the 4th, like that. Our degree is 4, and our coefficient, our leading coefficient, is going to be negative for that fourth degree term. Therefore, we will have the end behavior of a negative x to the fourth. And remember, x squared, x to the fourth has, and if it's negative, it has this end behavior. Down to the left, down to the right. Okay, so that's what our end behavior is going to look like. So that part's done. And now we will need to graph this thing. So let's get that done quickly. And all right, so let's put our roots in there. So we have a single at x equals 0. All right, so single. All right, x equals 0. And we're going to have a triple out here at x equals 5. All right, I'm going to, we'll label that in, we'll go ahead and label it triple x equals 5. All right, so let's put our end behavior in here. We may have to move it in a minute. I'm going to go ahead and put it in like this, and then it's got to be down this way as well. All right, so the only way that we can have a single root, so we've got to pass through the x-axis right here, and then we need a triple right here. Along with this end behavior is we're going to have to come up here. We're going to cross completely through, so that's our single root. Then we're going to have to curve back down. How high this curve down occurs, we don't know right now. Again, when you get to calculus, you'll be able to find that. We're not too concerned about it right now. So we've got to curve down at some area. We don't have to label this. So we're curving back down, and then we need to have a triple root here. So that's this thing where we have a change in concavity. So we're going to put that, I'm going to exaggerate it a little bit, that change in concavity, and then drop down like this. All right, so it would actually have been better if I would have wrote this up here. So that's our triple root right there at x equals 5. Remember, that's the change in concavity, so we're concave up right here, and then we change the concave down right there. That's our point of inflection at x equals 5. All right, so that part is done, and we're going to call this video good, and I'm actually going to work 2 more from what will be your homework, where we actually have to factor first. On all of these examples, we haven't had to factor first yet. So I'm going to work 2 more in this last video for this lesson. All right, so I'll see you in the next video.